The topic is about Constexpr and also about consteval and constinit specifiers. Actually, it's a pretty simple topic, and the definition in the standard it says that says exactly that Constexpr specifier declares that it is possible to evaluate the value or the function at compile time. Such variables and functions can be used where only compile time constants expressions are allowed. And a little disclaimer that if Constexpr is slightly different language element, it's not that modifier. I think I will cover it briefly later in the different talk. So what we have from that definition, that Constexpr are useful when so the usage of that is to use them in compile time expressions. What are they? It turns out that there are very few of them syntax-wise. It's explicit template instantiations, template specializations, and default template parameters. In other words, it's everything that goes into within angle brackets. It's array type declarations and its static assets. So, do we have any other cases where Constexpr are useful? And the answer is no. And this is important remark, because there is some people have misunderstanding that if you annotate all your functions as Constexpr, you will gain something, or your runtime code will be faster. This is not the case. The Constexpr specifier is only useful for those concrete cases. That's it. Now the dumb examples of the cases where Constexpr is useful. Okay, so this is our Constexpr variable, Constexpr function. So the first case inside angle brackets, we can use that and that and that. We can also use it in array type specifiers and in static assets. Let's go with less dumb example. Assume that we have something like CUDA program environment where we our data should be aligned into some big chunks of memory. Well, for example, in CUDA, the spec says that this alignment should be 1 to 28. And what we want to do, if we create some CRA, we want this CRA to be automatically the innermost. We want the innermost dimension of this CRA to be automatically aligned with those requirements. So that suppose we will have some meta function that it is, in my example, I called it expand t, So we applied this meta function to the array type, and we return another array type where the innermost dimension is aligned. Here, you see that aligning of the float and double arrays is different because because float and double can have different sizes. So how can we do that? We can we will do it with sorry. I lost a little bit. We will do it with specialization of our template. So if the type that we are going to expand is not an array, we just return this type. If we have an array, we are doing our expansion, and we delegate it to some function that is Constexpr. Why it should be Constexpr? Because it appears in the declaration of the array type. So by default, it should be Constexpr. So what we are doing here, we have the size of the element and our alignments in bytes, and we take LCM. It's least common multiplier. It's a standard function, and luckily it's also Constexpr. And by dividing by size, we have the size of the unit where it should be alignment, and we do alignment, do expansion. So also we have this recursive function that does the work where our array is multi-dimensional. So what we can see from that example, so that sometimes the calculations that we need is quite complex. For example, if we don't have, if we will not have this large least common multiplier in the standard library, this algorithm requires some loops. So it's well, it's not trivial to do in a manner that that Mauro demonstrated to you in the previous talk with the factorial example. So that's the motivation. Okay, let's take let's take another example. If we will go to the definition, we can see that nothing stops us from using Constexpr functions from the runtime context. So let's model that situation. Let's let's assume that we have some Constexpr function foo that we are going to use everywhere. We are going to use it in the constant evaluation context, like here, and in runtime as well. And for the runtime, we are going to do runtime tracing. Here is the simple tracing utility. It, by the way, demonstrates the C++20 way of querying the position in the source code. There's this std source location structure, and this that has current static method that returns the current position, and we can grab file name, line, column, and the function name from that, and it's quite useful. And and by the way, this example demonstrates how the default parameters of the function is evaluated. When the function is called, this is the place where this default parameter is evaluated, so not in the function definition. So this location will take place in that line, so not in the line where the trace function is defined. So what we see additionally, that from C++20 there is the possibility to determine from within the function in what context we are currently evaluating. We just can query that with this isConstant evaluated function. So what we do that, here, if the function is not constant evaluated, we are just tracing it. The output is what we can expect. So the first call is will not cause the tracing, and the second call leads to the tracing. Okay, that's good, but let's do the following thing. Let's change Constexpr definition of our function to consteval. Now we don't have output, but all our asserts are still good. What happens here? Consteval forces the function to be evaluated only in compile time. So if function is declared as consteval, it cannot be evaluated in runtime. So even if this is a runtime context, we compiler if it can tries to evaluate it, it forces evaluation in compile time. So, but luckily in this example, it's possible because arguments are the argument is just literal. But what if we will try to modify this example and to add this new function invocation that will take runtime parameter. Here TMP is declared as not consteval. Yes, we will have an error that is quite readable. That the TMP is not usable in constant expression, obviously. But wait, probably we want to benefit from what if we want to benefit from both? We want our function foo to be such that in constant evaluation it works. If it can work in if it can work if it has if it has literals as a parameters, it's also evaluated to constant, and it can work in that way. Can we do that? Apparently we can with some trick. Let's define a helper. I'm calling it as consteval, and this helper just returns its argument and has consteval function, consteval specifier. So now we and let's do our and let's return Constexpr modifier to the original foo function. Now we can do this fine tuning for the foo call. We can use it pure. With this modifier, we can decide where we want to evaluate that. Okay, next thing, I don't really want to spend time on it. It's consteval modifier. So this is the definition that is in the standards. It asserts that a variable variable has static initialization, and means that it either zero initialization or constant initialization. Otherwise, we will have an error. But the only usage that I'm aware about is to fight against the static initialization or the fiasco. And I don't think that this. I don't. So honestly, I don't think that this is the common case for the developers, and I prefer just to skip that. Please Google the manual. Oh well. At the end, I have this fun example that I come up with. Okay, so I have a function that just returns etc. The strange thing about this function, this snippet compiles, but what about moving one line, moving this start assert one line down? Now we have an error. Let's explore what happens. default parameter of this function is its source location, and source location is the thing that basically all methods within source locations are declared Constexpr. So we that's why it can be called within static assert without problems. And but the logic is the following: if the line where our function is defined is even, we call another function f. That is not Constexpr. So and obviously for the even number 11 we have this arrow, yes. But if we move it back to the line number 10, we don't have. So this demonstrates that compiler is quite smart to detect if your function can be evaluated in constant in compile time expression or not. So compiler basically in this case where there are no asserts, compiler basically goes inside the function and concludes that even though this function is called non-Constexpr function, it's okay because the parameter is such that this branch is not evaluated. I think that's it. Okay, I have some comments here. Yes, so the comment was about about the default alignment in CUDA. Of course, in my example, it was just simplification of the it was just simplification. Also, I added the possibility to specify the concrete default alignment. Okay.